Metadata.
including the fact that it's a regular file. Okay? Now that it's a regular file, what am I going to find down here?
The data?
I'm going to find, in this case, 4 blocks, because we decided it was 4K per block, and it was a 16 kilobyte file. So I would find, as an example, 7, 9,
41
41,
and 733.
and 733. And these would be sequential. So first I'd grab block 7, and that would be the first piece of my file.
Mm-hmm.
Then I would grab block 9, and that would be the next piece of my file. Then I'd grab block 41, that would be the next piece of my file, each of these being 4K, 4K, 4K. And now, depending on what size it says up here, right?
Right.
What's the largest size that 4 blocks could accommodate?
4K.
16K, 4 apiece. What if it were 15K? I'd still need 4 blocks, but only part of the last block would be used. And that's what size tells you. So is this clear now? So it's a 2-step process. inode, block.
I need you to go back to.
Inode, block.
I need you to go back to 110.94.1104 G.text. How did we know it was a file?
This is the inode that corresponds to GRM, and it happened to be 110 inode.
Correct.
So, and remember, where did I get that from? I got it from the block here. It said, I'm sorry, I said 110. It should have been 74, shouldn't it? Did I goof it up?
You got 110 above.
No, the last block was 74. GRM was 70.
Yes. All right. So, I find the name of the file here. And what does this number represent?
The inode.
The inode for that file. So I go to inode 1104 and I find this thing. The upper piece is the metadata. The lower piece are the block addresses containing the data.
That G1.text, that's the actual name of the file, right?
That's where the name of the file is contained,
Okay.
Q1.text. All right. Now, up until now, we've consistently pulled back data blocks that corresponded to directory files. Now we're pulling back data blocks that correspond to regular files. Question?
So this structure of Unix file system,
Yes.
inode and block and data block.
Yes. Now, what if there were, let's say, a total of 10 addresses down here? Suppose that there were only 10 addresses in the inode. What's the largest file that we could deal with under those circumstances if each is 4K? And there's 10 of them.
40.
Times 10, which is?
40K.
40K. That's not a very big file, is it? Okay? So, if the file size exceeds the capacity of the direct data blocks, then you can use what are called indirect data blocks. So rather than the data blocks containing data, they contain more block addresses. Right?
So they have data too, right?
They could have data, but no, they contain, an indirect block contains block addresses. So suppose that a data block could hold 100 block addresses. Now what's the largest file that we have? If a data block could hold 100 block addresses, well, let's see. So first of all, each of these 10 addresses would reference a block, which is an indirect block, right? So there would be 10 indirect blocks, right? Then each indirect block would have how many addresses? 100. 100. So 10 times 100 times 4K. So suddenly, I've now got 4 megs. by using this idea of a direct block. So, inode block. By the way, more than one. Right, up to however many go. The other case is inode, then indirect block, and then block, 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 block. You see it? So let's do a simple case. Suppose that the inodes hold 4 addresses. Suppose the inode holds, let me erase some of this. Can I do it over here? Is this all right? Can you guys see all right? Because I know this thing in the way kind of makes it tough. So suppose that a data block is 2K. Suppose an inode holds 4 addresses. And suppose that a data block, in addition to holding 2K of data, suppose that a data block can also hold 8 addresses. What's the largest file that we could have in this system? What's the largest file? Let's sketch it out first. Where does it always start?
At the
inode. So here I've got the inode, right? And then metadata. How many block addresses can I have? According to this.
4.
4 of them. So I've got 1 address, 2 addresses, 3 addresses. I've got 4 addresses, right? Now each of those points to a data block, right? So this one points to a
2
data block. But what does that data block contain?
metadata and
8 addresses. So look, 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Then finally,
32.
1, 2, 3, 4, 5, 6, 7, 8. Now each of these points to what? A block. Do you see it? So how big is this?
2K.
2K times
4. 8.
8. So that's
16.
64K.
16 plus 16 plus 16
48.
plus 16.
64.
64K. So in this example, the file, oh wait a minute, gee. 1, 2, 3, 4, 5, 6, 7, 8. Double indirect, triple indirect, quadruple indirect.
So is there a limit to how many indirects you can have?
What's that?
Is there a limit to how many indirects you can have?
In any given implementation of an old-style Unix file system, the answer is yes. Okay.
Just use more blocks, right?
It's usually driven by the maximum size of an integer that you can keep.
See, thank you.
Some characteristic of the file. So here we go. So how do we create a small file? Here's the algorithm. So we're starting out from scratch. So what's in my memory space right now?
Nothing.
The directory listing for the current working directory, the list of inodes that are free, and the list of blocks that are free. Those are the 3 data structures that are at my disposal. So what's the first thing that we do? If I'm going to create a small file. Here we go. Find a free inode number in the inode list. So I go to the operating system and go, I need an inode. And the operating system walks the inode list and goes, here you go. And it gives me an inode number. Now what do I do with that inode number? I tell the operating system, okay, take it off the free list so no one else gets it. So now that inode number is no longer on the free list. Then what happens? I need to know how big is my file. So that can tell me how many blocks I need, right? If it's a small file, I know by simply looking at the block size. So however many blocks I need, I grab them. Then what do? I tell the operating, so that step is I go to the operating system and go, hey, I need some free blocks, man. Give me some free blocks. So he gives me my free blocks. And then he takes them off the free block list, right?
What's wrong with you?
All right, so then what do? You record the data in those blocks.
You're not in trouble.
So there's, inside the operating system, there is an image of what the block will look like. And I record in those memory spots inside the operating system the data that's of interest. Say it took 4 blocks. So I'm going to have 4, what will ultimately end up being images of the block in the memory of the operating system. I load that data up into those images of the blocks. And what do? Flush those data blocks to the disk. So now the four blocks that I requested, I've loaded up their in-memory image, and I've placed them on the hard drive where they're supposed to go, depending on what block numbers the operating system gave to me. Then what's the next thing I do? I record the file attributes in the inode because I've got now an in-memory image of the inode. So it's a regular file. When was the timestamp? Right now. I would give it whatever the default permissions are. That's set by my umask command. Okay. I would tell it the size, blah, blah, blah. Record all this information in the inode, including what? Including the block addresses that it gave me. Record the 4 block addresses. And then what do? I flush that inode out to disk. So I take this in-memory image of the inode that I've constructed, squirt it out to the inode on the hard drive, and then finally what? Record the file name and the inode number in my current working directory, and possibly flush it if necessary.
You have to explain flush.
Write it out.
Okay.
To write it out to disk. So that's creating a small file. Okay? Let's walk through that process real quickly.
You're not in trouble. Stop tripping.
So, Doc, if you wanted to know the specific address, then all you have to do is know where it falls in your block of data, right?
So yes, so there are ways in the operating system where you can query it and find out, what inode it's at. And if you know how the hard drive is constructed, then you could actually go out using raw data manipulation mechanism and read the hard drive.
Dr. Morris, but you know what's got me confused? Because when our last discussion, we was talking about everything started with the root.
Well, it did ultimately, because I had to get from root down to GRM, didn't I?
Yes.
So, but remember, you have this idea of what's called current working directory, which is the directory file of the directory where I'm working. Okay,
Root's the first inode, right? Root's the first inode.
It's root. Okay.
Isn't it, Dr. Morris?
Yes.
The root's the first inode, right? Root is the first inode. Our first inode is the root.
Yes.
So basically,
You walk from there.
So the first 0
Yes.
is still root.
Yes.
I know this
the way
root.
we've constructed it. I mean, it doesn't have to be 0. It could be anything that the operating system knows. We could agree it's going to be at 0. We could agree it's at 20. I just picked 0 because it's a nice place to start. We agree that the root inode is at 0 because otherwise you wouldn't know where to start. Right?
Right.
So let's construct. Suppose we had this scenario. Suppose we had slash which is at 0, and we have user. Suppose that's at 12, and then down here I've got stuff.txt that I'm going to create. I'm going to create a file called stuff.txt. I'm going to put it in /user. All right? That's the idea. I'm going to create this small file.
Okay.
Following this algorithm. So first of all, I'm already in the directory called user. Yes? So that means, how did I get there? I picked inode 0 and found in it the inode for user. Okay, when I found user's inode at location 12, I picked out inode 12 and it said data block 47 contains the directory listing for the directory called user. So in my memory space, I've now got this directory file for the directory called user. All right, and it's going to have dot, which is 12, dot dot, which is 0, and the rest is going to, let's say there's nothing else there yet, it's empty. All right, in addition to this directory listing in the operating system's internal data structure, there's also going to be some list of inodes that are free, and there's going to be some list of blocks that are free. For the sake of argument, let's say that the data file called stuff.txt is going to take 2 data blocks. Let's say that this guy here requires 2 data blocks. Let's say that's how big the file is. Suppose that the inodes that are free are 7, 14, 31, 87. Suppose the blocks that are free are 111, 4102, 79, 793. So those are the data blocks that are free. So there's my 3 data structures. I've got the directory listing of my current working directory. I've got a list of inodes, and I've got a list of blocks. All right? In my program, I've got a program running. It's going to create a file called stuff.txt. And it's going to do it in the current working directory. What's the first step?
Find a free inode.
I need an inode, so I go to the operating system. Umar, you're my inode deliverer. I need an inode number, dude. What are you going to do?
I'm going to give you 2 inode numbers.
Just one. All I need is one.
Oh, okay.
I need an inode number, so give me one.
44.
Okay. Well, it's not on the free list, okay?
Oh, okay. That's 14. Okay, 14.
So you're going to give me inode 14? So you take inode 14 off the list, and now inside my context, I know that I have inode 14. Inode 4. This is the in-memory image of it. Okay, it's an in-memory image of it, inode 14. And of course, now that's been removed from the free list. Now what's the next thing I need?
You need to find a block.
I know that my file needs 2 blocks. So I'm going to go to my block deliverer. You're the operating system kernel that delivers free block addresses to me. I need 2 blocks. What are you going to give me? Okay, so 111 and 4102. 111, 4102. So I know immediately 111, 4102. I'm doing it a little out of order. Those are going to go in the block addresses in my inode, correct? And now what do? Take them off, then I record the data. So now I have, for each of these blocks, an image of the block in memory. Okay? So this is not yet, but ultimately this is going to go to block 111, and ultimately this is going to go to block 4102. And then I load it up with whatever my data is. Boom, boom. So now I have an in-memory image, let's say. It could do it directly, it doesn't matter. An in-memory image of my 2 blocks. Then what do?
Flush the data block.
I flush those data blocks out to disk. So it takes these 2 data blocks, and I tell it, write this guy to 111. So it's going to go out to my data block 111, and it's going to record that data there. And then it's going to say block 4102, and it's going to write that data there. So now the data for my file, stuff.txt, lives out on the hard drive. The data's there. Now what's the next thing I do?
Flush the data, record
Well, I
the...
just did that. Record the file attributes in the inode. So I come into the inode and I say, gee, it's a regular file. The timestamp is now. The permissions are read, write, execute, read, write, execute, read, write, execute, and whatever else. So
But Dr. Morris, why wouldn't you put that? Why wouldn't you put the information about the metadata? Excuse me, the metadata
first?
with the file. I mean,
It is with the file. It's with the file's inode. The data and the inode are separate things. Look, you are not Kristen. That's simply a tag that I use to associate you. You are this stuff.
Right.
That's you, not Kristen Howard.
Okay.
Kristen Howard's simply metadata. It's a way of identifying you. It's not who you are.
Okay.
Right? So the data is what the file is. The inode is metadata about the file. Okay, so I record all the attributes. Okay, and then what do I do?
Record data block versus in the inode.
So, which I've just done.
And then flush the inodes to disk.
So now I take this inode 14 right here, and I flush inode 14 out to the disk. So this is inode 14. This is block 111. This is block 4102. All right. Then what do I do?
Record file name and inode number in
So I come over to the user file directory, and I go stuff.txt. And what inode does he have? He has inode
14.
14, right? And then if I was getting ready to change the working directory, I would flush this to his data blocks, right? Then I would change his inode to record the new timestamp, blah, 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 blah. So there's a lot of detail that's missing here, but it's always a two-step, right? Yes.
Now, when we're doing all this process, now these data blocks and this inode number, they're also going into the physical memory. I mean, they're also going into the RAM because obviously that's where they're being processed. I mean,
Yes.
right?
Yes.
They're going back and forth. All the time.
Absolutely. Operating system structures. These are all kept in operating systems. So that's creating a small file. Let's move on and do now a large file. So we won't do all the details, but it should be obvious. So what's the first thing I need for any file?
Find a free
An
inode.
inode.
Yeah, no.
Need an inode. Bam, you give me an inode. Pull it off the list. Tell me it's no longer free. Then what?
You need some blocks.
I need some blocks, first of all, for the indirect blocks and for the data blocks. And that's just an arithmetic calculation, right? Suppose that, and you'd have to know that, you'd have to know that a data block is, say 8K, and an indirect block is, say, 32 addresses, right? And if the file's too big, and then how many inode addresses? So inode addresses, you just see this is suppose that the inode could only hold 4 addresses. What's the biggest direct access file that I could have? 4 by 8, which is 32, right? So if my file's bigger than 32K, what do I know I need to do?
Indirect blocks.
Indirect blocks. So I'm going to say, okay, so each of these now can hold 32. Suppose the file was 128K. That's how big my file is. Let's figure out what we need. All right?
You need 4 data blocks. I mean, you need.
So let's see. Now, so ultimately, I'm going to need. How many is this? What's
8.
128 divided by 8?
4 by 32.
I don't know.
Hold on, I'm going to tell you.
It's 2 to the third
16.
and
16.
1, 2, 4, 2, 4, 8, 16, 30, 7. 2 to the 7, so 16. See, why didn't you say that?
I say 16.
Right, so it's going to take how many data blocks?
16.
To record 128K of data, how many blocks?
16.
16 blocks, right? So I know that I'm going to need 16 data blocks. How many indirect blocks am I going to need?
16.
Just one.
Just one.
Because each indirect can hold 32. Do you see it? So I'm going to need a total of 1 indirect block and 16 direct blocks. Total of 17 blocks. So when this thing's all said and done, what's it going to look like? Here's going to be the inode. It's going to have 1 indirect block, right? That points out to here. And that guy's going to have what? 8. 8, and each of those, no, I'm sorry, 32. It's going to have 32 of them. So 0 through 31 addresses.
But why
Right?
32? Why not 17? Because we only have 17 blocks.
This is how many it could hold.
Ah, but it's gonna have 17 on
But
it.
it's only going to have populated 0 through 16.
Okay.
Excuse me, 0 through 15, which is the 16 that I need. So there's one block here for the indirect, right? And then 16 blocks for the data. Is it clear?
No.
Now let's follow it through. Here we go.
Dr. Morris, no. So each block is going to have 32 addresses.
Up to 32.
And that's going to add up to 8K.
Well, no. Each of these individual addresses holds up to 8K.
Okay, got you.
So I've got 16 times 8, which is 128K.
Okay.
All right, so here we go. Find the free blocks for the indirect blocks. How many do I need?
1.
We needed 1. So bam, I get my free block. I call that my indirect block. Then what do I need? I need how many data blocks? 16 of them. I need 16 block addresses, so I get those. I take all that stuff off the block list, the free block list, and what do? Record the data in the data blocks. All 16 blocks get loaded up with the data. Then what do? Flush those data blocks out. Then what?
Record the data
block addresses into the indirect data blocks. Okay, then flush the indirect blocks out. Then I update the indirect block address in the inode, flush the inode, then I record the file name of the inode in the directory table, okay, and possibly update the metadata in the directory file tables inode. Because remember, the only thing that's going in the directory table is data. So by adding a new name to it, I've changed its size, I've changed its permission, I've changed its access times and all that. But I left all that off just to. So that's creating a large file. How about deleting a small file? Let's see if this all makes sense. First thing we do is we find the file name in the directory table. As soon as I know the file name, what else do I know? The inode number. So I go out to the disk and I grab the inode number. Then what do? I read the contents of that inode into memory so I know what's there. And then what do? For each data block address in the inode, I tell the operating system, I'm done with this data block here.
Make it free.
Put it on the free list. Notice that it doesn't delete the data.
Okay, so it'll be rewritten, basically?
Hopefully someone later will overwrite it. Otherwise, it's still there.
Right, that's how the perverts get caught.
There's many fellows in jail with their kiddie porn because they didn't know this. Okay, had they taken my class, they would be free men today. Okay.
Now let's leave perverts where they belong.
So when we delete, we just make it available and we just flip the bits in there?
Yes, there are secure operating systems that say prior to putting them on the free list, Mr. Operating System, you go out to that data block and you flip it 150 times, randomly 0, 1, 0, 1, 0, 1, every single spot on the hard drive, so that this reluctance, this tendency to know that it used to be a 0 is eliminated.
But for us, for our systems, we wouldn't do it, right?
Standard operating systems
No.
don't do that. It'd kill you. I mean, every time you created a file, it'd be a 10-minute process. Because it takes, remember, what's the access speed of a hard drive? Milliseconds. So you'd be waiting there 100 flips of a 4 meg file. Come on. That's why we grind up hard drives at work, rather than give them away to the school.
Because we an option if you want to do it.
No, because all it would take is one oops. And suddenly we're on the front page of the Washington Post. Army Corps of Engineers releases sensitive data to Al-Qaeda.
And everybody there will have to go to the FBI and get shook down before you be free.
I'm serious. Yeah. Now forget it. We're going to grind it up. That way we know it will never be released.